Neuroplasticity is a term that's becoming more well recognized, certainly in the academic community and also in the layperson community. And I want to try to explain what neuroplasticity is. It really is not that complicated. It's not like the plastic bumper of your car, but plasticity for me refers to a brain that is highly dynamic and constantly reorganizing and malleable. So in other words, it can be shaped. And one way it can be shaped is by environmental input. Now, historically, we have followed a traditional thought about the human brain, which is that in the womb you develop millions, if not billions, of brain cells. And even in the womb, there's a type of civil war taking place where those neurons, as we call them, brain cells, neurons, are fighting each other off. So only so many survive as you're born. And you, like me, we were probably all taught that you're only given so many brain cells once you come out of the womb, and that you lose brain cells on a daily basis. Now, you have enough of them, certainly, to do what it is you need to do in life, but the thought was always that you don't get any brain cells back once you're born and once you lose them. And that was more of a rigid, kind of downward spiraling model for the human brain. Well, neuroplasticity is exactly the opposite now, isn't it? Because we're talking about a brain that can be changed over time, and a brain that indeed we think now not only loses brain cells, but can regenerate brain cells. It was in 1998, the first study of its kind by some authors in San Diego as well as in Europe, where a study was published that looked at 5 brains. These were at autopsy. And what they discovered was that the human brain was able to generate new brain cells. And they found this regeneration of neurons in a very specific part of the brain called the hippocampus. Now, your hippocampus is important to you because it's the part of your brain which sits just under each temple in a part of the brain called the temporal lobe. And the hippocampus is the structure that helps you learn new information. That's what the hippocampus does. It takes information in for you, hangs on to that information. If you think it's important, it'll transition that information permanently into that outer shell we call the cortex, C-O-R-T-E-X. And there, information is stored permanently. You've heard of long-term memory. Now, whether or not we have access to it as we get a little bit older, some of you who are a little bit older might have struggled a little bit with coming up with somebody's name or remembering an event or a piece of information, but you have access to it once you're given cues and prompts you'll recognize. And that tells you that your hippocampus is doing what it's supposed to be doing, which is learning new information. You know, in the 1950s, there were some studies done on rodents. This is very interesting. And what they did, these scientists out at Cal Berkeley, is they took some rodents and non-human primates and they placed them in one of 2 environments. One was called an enriched environment and one was called an unenriched environment. And they looked at the brains of these 2 different animals at autopsy. And it turns out that the animals that were raised in the enriched environment had a significantly larger brain compared to the animals raised in the unenriched environment. The second major finding was that the animals raised in the enriched environment had many more brain cells and new brain cells. Guess where the new brain cells were found? In the hippocampus. That structure we just talked about that helps us learn new information. Those animals raised in the unenriched environment had significantly fewer brain cells and really didn't generate new brain cells. The third major finding was that the animals had many more cellular connections. We call that a synapse. That's how your cells communicate with each other. Cells in the brain never touch each other, but they get real close. And the more connections there are between brain cells, really it's a sign of brain health. The animals raised in the enriched environment had many more synaptic connections relative to the animals raised in isolation. Now, if you will for a second, think about a brain that has a tremendous number of cellular connections or has what we call synaptic density. That's a sign of brain health for this very practical reason. The more connections you have in your brain, we call that brain reserve, the greater brain reserve you have. The way I like to describe it, for people that really don't think about the brain a whole lot, is Imagine flying over 500 feet in a plane and you're looking down at a jungle. We all have that image in our mind. By the way, robots can't imagine that. Then imagine flying over an island where there is one palm tree. You can kind of picture that in your brain as well. Now, if you just follow me along with this simplistic example, think about Alzheimer's disease, that very cruel progressive dementia we all know about, as a weed whacker. And I don't mean to be funny with this. Weed whacker comes in and it takes out weeds. In this case, a weed whacker, Alzheimer's disease, robs you or takes out brain cells. If you think about this example, we all want our brain to have tremendous reserve. We want our brain to look like a jungle because Alzheimer's disease will come in and do its damage. But if you have tremendous reserve, if you have tremendous number of cellular connections, it's going to take Alzheimer's disease a lot longer to demonstrate its clinical phase, to manifest the symptoms. And the real miracle of this brain reserve story is that, you know, today we know from studies that at autopsy, there are brains, and really a significant number of brains, diagnosed with Alzheimer's disease. That is, they have the pathologic neurophysiological markers of Alzheimer's, because we know what those are. So at autopsy, the neuropathologist will diagnose Alzheimer's. Then what they do is they go back and they say, okay, for this brain diagnosed with Alzheimer's, what did the person demonstrate in life? When did the disease manifest? Behaviorally. And it turns out a large number of the brains diagnosed with Alzheimer's at death never manifested the disease in life. They were healthy till the day they died, functioning independently or semi-independently. And so we're trying to explain that. How can that be? A brain diagnosed with Alzheimer's at death with the clinical markers of Alzheimer's at death, at autopsy, not show the signs of Alzheimer's in life. And we think one of the real reasons is the person had tremendous reserve built up. And how do they get the reserve? They continuously, across their lifespan, expose their brain to what I call novel and complex environments, which helps to build up those cellular connections so important to building brain reserve and brain health. Now, in terms of the enriched environment, that sounds nice. What does it mean? Well, I went back and read some of that research. And really what I learned from the scientists who did this research back in the 1950s until today is that three critical factors emerged that really defined an enriched environment. One was socialization. That is, animals had to have other animals of its kind in the environment for it to be enriched. The unenriched environment, the animals were in isolation. They were all alone. The second major factor was physical activity. Literally, they had a running wheel that the animal ran on. I'll bet you don't think of the gerbil in your son or daughter's bedroom running on the running wheel as engaged in brain health, but really that's what's happening. And in fact, running itself in the animal model has been shown to lead to new brain cell development. It was kind of interesting. The third major factor was mental stimulation, and these scientists defined mental stimulation by having toys and things in the environment the animal could interact with. The animal in the unenriched environment didn't have a running wheel and no toys, and remember, they were in isolation. So you get a sense of the real difference between an unenriched and enriched environment. So three critical factors: socialization, physical activity, and mental stimulation. Now remember, we've learned recently that the human brain also has the capacity for plasticity and to generate new brain cells. So it begs the question, how can a human brain that has a capacity to generate new brain cells do so? What do I need to do to generate new brain cells? Well, even though we don't have the conclusion, it makes sense to go back to the animal model. Think about the enriched environment. Our three factors: socialization, physical activity, and mental stimulation. There are two other factors that I think are critical for the human brain that I propose as being important and necessary for brain health promotion across the lifespan. Those include diet and spirituality. So when you think about it, for the human brain, from a brain health perspective, there's five critical factors: socialization, physical activity, mental stimulation, spirituality, and diet. In much the way we have five fingers, You know, your fingers don't work in isolation. They form a hand. And you can make your hand into a fist that becomes whole. And so what our goal with a brain health perspective, and health indeed, is to be holy, which comes from whole, to be whole. Most of us, if not all of us, are fragmented in some ways. And so a goal throughout life becomes, for each of us, to fill in, to complete where we have fragmentation. One of the beautiful things about the brain health program that we're talking about today is you can actually look at your own portfolio, your own pie, as I call it, 5 slices of the pie. And where are you strong? And where are you weak? And where can you make changes within those 5 critical factors to enhance and maximize brain health? Because remember, along the way, as you engage in an enriched environment, in the novel and complex environment, you're building a brain that looks like a jungle to fight off neurodegeneration should it enter into your cortex.